Hello everyone, welcome to the on-demand part of APSC 174, the final exam session. I just wanted to let you know that these are the topics that I reviewed with you here. Basically all the topics of midterm 1 and midterm 2. I'm still going to go over some of those during the final exam session. Definitely we're going to revisit some of the concepts. But in here I tried to review just a little bit of the theory, not a lot of theory, and then a lot of practice problem. You'll see later when you look at the video, there's tons and tons and tons of practice. There's 33 pages. You can see the page number over my shoulder, this shoulder. So there's 33 pages of just practice problems with not a lot of theory, but the basic theory, just to help you study for this really quick. So these are the topics I've covered, and I'm gonna go over some of them again briefly when we encounter them during the live session. I mean, by now you would have been to the live session probably, so I'm talking about my future, which is your past. It gets, the timeline gets messy with this. So anyway, these are the topics that I worked on. These are the problems that you will see here. If you have any questions, any comments, please do not hesitate to email me at antoine@prep101.com. If there is any typos in there, or like I do 1 + 1 is 5 sometimes, please, if I didn't find it, I apologize. I obviously didn't do it on purpose. Don't let it shake your understanding of the mathematical world. Thank you for watching this. Thank you for taking the time, and I wish you good luck on your test. So we begin with the concept of vector spaces. Now, for the final exam, we're not going to go through much in this. We're just going to say that vector spaces are sets, that it's a set V with two operations, the addition of vectors and multiplication with a scalar, and it satisfies all of these 10 properties. We've looked over this in midterm 1 in more details. For now, we're going to focus on the questions that are more likely to show up on the final exam, and that is the question of subspaces. So, what is a subspace? A subspace, I'll maybe explain here a little bit. So, when we say a subspace, that's a space within a space. So, W is a subspace from now on, SS of V. It means W is a vector space, so it satisfies all the properties of a vector space, but it also is part of it's part of V, which is a bigger vector space. Now we know that if W is in V, it's the subspace of V. That means the dimension of W is less than or equal to the dimension of V. Now, if the dimension of W is the same thing as the dimension of V, that would be that means that W is in fact V. What is dimension? We covered this in the midterm 2 session. I will say it in more details later. Basically, it's the number of vectors in the basis. So the dimension is the number of vectors in the basis. You can think of it as the maximum number of linearly independent vectors. It has many meanings. For us now, it's just how many vectors are there in a basis for V. For example, the dimension of R3, let's say, I'll give you a quick example here. The dimension of R3, that would be 3. So that means in any basis of R3, you're going to have three vectors which are linearly independent and they span the space. Again, we're going to talk more about that side of the subspaces, dimension, basis, and linear independence later. For now, I want to focus on how do we test that a subset W is a subspace of V. Now we need to check 3 conditions. So to check that W is a subspace of V, it must satisfy that the 0 of V, the 0 vector belongs to W. So it must contain the 0 vector. It must be closed under addition. So that means if I take vector W1 in W and I take W2 in W, that means if I take W1 plus W2, I'm going to be in W. I should decide whether to use the symbol or say in, so let's just use in W. right? And then it has to be closed under scalar multiplication. Under scalar multiplication, where do we write it? So that means if I take W in W, if I take K times W, KW is in W. Again, I'm mixing up notations, I'll fix it, right? So to check that a subset is a subspace of the whole space, of the vector space V, we need to check that it contains the zero vector, we need to check that it's closed under addition, and we need to check that it's closed under scalar multiplication. Now, we're gonna practice some questions. In some instances, there will be questions that have to do with other parts of the course, things that we've covered in chapter 1, in midterm 1 or in midterm 2. I will solve them, and I will try and include as many details in the solutions as possible. So let's see. This is in a final for 2019. APSC 174 used to have finals, but then for a while it used to have midterm 3s. So 2020, 2021, 22, they had midterm 3s, and now we're back to the final exams. So I picked some finals from 2019 and older to review these topics with you, because that as of 2020 till 2022, those topics were not included on the final. It was just a midterm 3, and then the topics were only after midterm 2. So let's consider C infinity R, which is the vector space of all functions that have derivatives of arbitrary order. So all the functions that you can find the derivative infinitely. It's known that this is a vector space, and let's take a W, a subset of, let's call this V. I don't want to say C infinity R every time, so C infinity R is V. So W is a subset of V, such that when you take the derivative of any element in W, you're going to get 2x times f of x. If you think about it for 2 seconds, basically those are all the functions where the inside is x squared. So sine x squared, ex squared, cos x squared, right? Because of chain rule, you multiply by 2x on the outside. So to be clear, they gave you an example. So the derivative of e to the x squared is actually not all of them. Sine wouldn't work here because you want f prime to be 2x times f, so sine x squared wouldn't be in it. So it's a very restrictive subset. So anyway, e to the x squared is in it. We're not supposed to understand absolutely everything that's in W. We just need to understand what is W, and we'll try and prove if it's a subspace or not. So e to the x squared belongs to W, because when I derive e to the x squared, I get 2x e to the x squared, which means it's 2x times f of x. Sine x isn't, and as I was saying also, sine x squared wouldn't be. Sine x squared would not be a member of W, because when you derive sine of x squared, you get 2x times cosine of x squared. So you don't get 2x times f of x, right? So you get something else. So this doesn't belong to W, right? Is W a subspace? So condition 1. Does it contain the zero vector? Well, what is the zero vector? The zero vector is the function z of x equals to 0. Notice how I'm being cute and I called it z of x for zero vector. So z of x is the zero vector where it sends every x to 0. Now what's the derivative of z? Z prime of x, that's 0, which is in fact 2x times z of x. Right, 0 is 2x times 0. So that's perfect. Second item, is it closed under addition? So let's pick f of x belongs to W. That means that f prime of x is equal to 2x f of x. And let's pick g of x belongs to W. That means that g prime of x is equals to 2x g of x, right? That's what it means that functions belong to W. Now, when I add them, am I going to stay in W? So what is f plus g prime, again, of x? This would be f prime plus g prime, which would be 2x times f plus 2x times g, which we can write it as 2x times f plus g. So when you derive it, you get 2x times the original function. Therefore, f plus g, f of x plus g of x, does belong to w. Okay, let's examine, is it closed under scalar multiplication? So let's pick f of x in w. Again, what does it mean that it's in w? That means f prime of x is equal to 2x times f of x. This is what it means. So if I take alpha f of x, is it in w? Well, let me check. Alpha times f of x prime is equal to alpha times f prime. F prime is 2x times f of x. So I can write this as 2x times alpha f of x. So the derivative is 2x times the original function. Right? So this means alpha f of x belongs to w. Therefore, w is a subspace of C infinity R. Of course, maybe some of you are thinking, okay, what other than e to the power x squared is there? Well, you can take, I really can't think of anything else. If you take 3 to the x squared and you derive it, it isn't. So this is the only function that I think of that's inside of there. If I think of anything else, I will come back and mention it. But we don't really need to think of elements in W for now. We just proved that if there were elements in W, F and G, it's closed under addition. And if there's an element F in W, then alpha times F also belongs to W. And this is a subspace of C infinity R. Right, so let's turn our attention to this question. This is from a midterm of 2020. Remember, 2020 did not have a final. So we have a vector space R squared, as simple as R squared. The usual addition and scalar multiplication. Determine with proof whether this set H1 is a vector space. So it's all the elements in R2 such that y is bigger than or equal to x. Well, let's check. First of all, 0, 0, which is the 0 of this vector space, belongs to H1. Why? Because the 0 that's y is in fact bigger than or equal to 0 that's x. So that's the y and that's the x. And that's the least of your problems. Let's make it fail using scalar multiplication, let's say. So let's say 1, 2 belongs to H1, but minus 1 times 1, 2, which is minus 1 minus 2, does not belong to H1, because minus 2 isn't, so bigger than or equal to minus 1, it isn't. So this is not, H1 is not closed under scalar multiplication. If you must know, it's not closed also under addition. So just this is extra. You don't need to do both, but in case you wanted to check vector addition, if I take 1, 2, this belongs to H1. Now I need to add it to a vector. Actually, it will be. It is closed. Yeah, it is closed. So if you have, you don't actually need to check this because this will be true. But if you take x1, y1 belonging to H1, that means y1 is bigger than or equal to x1, and if you take x2, y2 belonging to h1, which means y2 is bigger than or equal to x2, then when you add them up, you're going to get the vector x1 plus x2, y1 plus y2. This will belong to h1 because y1 plus y2 is bigger than or equal to x1 plus x2, because this is bigger than this and this is bigger than this. So it is h1 is closed under addition. It's not closed under scalar multiplication. Okay, let's look at h2. So given the set h2, which is now y less than or equal to x, clearly h2 is also not a subspace of R2, because I mean, you could just give the same proof. But that's not what they're asking us. They're asking us, what's h1 intersecting h2? So what's h1 intersecting h2? So a vector xy belongs to h1. That means that y is bigger than or equal to x. A vector xy also belongs to h2. That means y is less than or equal to x. Now if it belongs to both, so xy would belong to h1 and or intersecting h2. What does it mean? It means y is equal to x. So h1 intersecting h2 is all the pairs. Wow, that switched so seamlessly to purple. It's all the pairs xy such that y equals to x. And is this a subspace of R2? That's definitely a subspace. So I don't know if you want to take a moment and try and prove that it's a subspace, if you could easily pause. So 0, 0 belongs to h1 intersecting h2, because clearly 0 is equal to 0. So h1 is h2 are all the vectors where the components are the same. So AA, BB, CC. So we can write h1 and h2, by the way, h1 intersecting h2 as all the vectors x, where x belongs to R, right? So if y is equal to x, then it's basically x. So y is the same thing as x. Now, so if you take a vector AA in h1 intersecting h2, and if you, AA, and if you take a vector BB in h1 intersecting h2, then clearly when you add them, you're going to get A plus B. This does belong to h1 intersecting h2, because A plus B, right? And then the third one, if you take a vector XX in h1 intersecting h2 and you multiply it by a scalar, you're going to get alpha x, and that's clearly in h1 intersecting h2, because it's the same component for x and y. Therefore, h1 intersecting h2 is a subspace of R2. Okay, I'm gonna just do a little bit extra from midterm 2. I know I haven't explained this in this session yet, but we did go over it in midterm 2. And if you don't understand this, then just wait a couple of minutes or so, and then I will do it in detail. What is this? What's the dimension of h1 intersecting h2? It's just too interesting to pass up. What would be the dimension of h1 intersecting h2? And if you think about it, h1 intersecting h2 is what? Is the span of what? Yes, it is xx, where x belongs to R. But let's write it a little bit more interesting than this. What's h1, h2? It's the span of the vector 1, 1. right? It's all like this. You can write it as x times 1, 1 for all the x's in R. So it's all the copies of the vector 1, 1, right? So maybe we write it in a nicer way. So it's the span of the vector 1, 1, right? So it's all the linear combinations of 1, 1. So 1, 1, 2, 2, 3, 3, root 2, root 2, 1 over 5, 1 over 5, whatever. So it's all the linear combinations of 1, 1. Therefore, 1, 1 would be a generating set for H1 intersecting A2. Since it's one vector, it's also linearly independent. It's linearly independent of itself. Therefore, if you want a basis for H1 intersecting H2, that would be just the vector 1, 1, which means the dimension of H1 intersecting H2 is 1 because there is one vector in the basis. Right? Again, I didn't explain those concepts in this session yet, but we did go over span in midterm 1, which was a free session, so I suppose everybody was there. And we just covered also span, linear independence, and basis in midterm 2. So if you were there, you saw explanations of this, and if you weren't, I will go over explanations of this a little bit later. So I'll take a short break from talking, and I'll come back very, very briefly. I mean, you won't feel anything because this is pre-recorded, and I will come back to finish this next problem. Next, before we practice more topics, I wanted to just go over with you some of the concepts. Maybe just go over the theory in summary so we know what we're talking about, because they're going to come up in many other problems, and I don't want to say like I'll explain it later every time. So let's just go through what does it mean that vectors span or are a generating set, what is linear independence, what is a basis, and what is dimension once and for all. And then when we solve problems, we can know that those definitions beforehand. Of course, those were done in the session 1 and session 2, so you may just know them. I'm going over them briefly now. So let's say, when we say vectors, so the first is the idea of span, right? Span or a generating set. So a span or a generating set, what does it mean? So we say that vectors v1 up to vk, let's say, we say that those vectors span a vector space, vs, don't forget vector space v, if the idea is that any vector in v is a linear combination of those vectors. If any vector, let's call it vector, I don't know, x in v can be written as a linear combination of the vectors v1 up to vk. In other words, more practically, there are constants a1 up to ak such that any x in v can be written as x is equal to a1 v1 plus a2 v2 plus all the way till ak vk. So any vector in the vector space v can be written as a linear combination of v1 up to vk. Some very important theorem. This is very important, and then I'm going to give you some examples of this. Let's say that v1 up to vk are a generating set for some vector space v, and let's say that the dimension of v is equal to n. Again, dimension is the number of vectors in a basis, or the maximum number of linearly independent vectors. It's very important to understand that if you have a generating set of a vector space that has dimension n, then you have at least n vectors. Then the k is bigger than or equal to n. You cannot generate a vector space of dimension n unless you have at least n vectors. Now, if you have n, they all must be linearly independent. If you have more, then you have to check that at least n of them are linearly independent. But for now, just let's take it to its most simple level. To create a generating set of a vector space of dimension n, you need at least n vectors. Now, that's not guaranteed that they will generate it if there's n vectors. We have to do a test. But at least we know that, let's say, 3 vectors cannot be a generating set for R4, let's say. Because R4 has dimension 4, so you need at least 4 vectors to start considering whether it's a generating set or not. Now, let me give you a couple of easy, and then we'll make them more and more difficult examples. For example, 1, 0 and 0, 1. This is a generating set for R2. Why? Because any vector in R2 can be written as a linear combination of 0, 1, 0, and 0, 1. Look, any vector AB in R2 can be written as AB is equal to A times 1, 0 plus B times 0, 1. Therefore, they are a generating set for R2. That's an easy example. Now, another example that also follows from this one and is also considered easy. Let's say 1, 0, 0, 1, and 2, 3. This is also a generating set for R2. Why? Because already this is a generating set. Already 1, 0, and 0, 1 are capable of generating all of R2. So if you add in 2, 3 to the mix, you still generate all of R2. So for example, any vector AB in R2 can be written as AB equals to this plus 0 times 2, 3. I mean, I found a way to write it. This is not unique here. This is not unique. There might be other ways of writing it as a linear combination, but I was able to write it as a linear combination, so those would span R2. Right? So to span, it's a to get a generating set, it's a loose concept. So this is why I say k is bigger than or equal to n. You can have more vectors than the dimension in a generating set. Right? Now, the next notion that I want to talk about is linear independence. So what does it mean that vectors are linearly independent? Right. Vectors v1 up to vk. So let's say the set is linearly independent. That means, guys, in English, this means that no vector is a linear combination of the other vectors. Not one of those vectors can be created using the other vectors. So, is a linearly independent set if no vi can be written as a linear combination of other v's. So not one of those vectors can be created by a linear combination of the others. Okay, meaning, the way to do this is the only, and this is a key word, only, the only solution to a1v1 plus a2v2 plus an vn is equal to 0 is a1 equals to 0, a2 equals to 0, all the way till an equals to 0. So there's no way that you could make those vectors combine and get the 0 vector except by choosing all the coefficients being 0. Let me explain this to you why. Okay. Let's pretend that you were able to find one other solution. So say you have 1v1 minus 2v2 plus v3 equals to 0. So say you were able to find one combination where the coefficients are not 0. Wouldn't that tell you that you can solve for v1? Wouldn't that tell you that v1 is 2v2 minus v3? I mean, you can solve for v1 or v2 or v3. You can solve for whichever one you want, right? So if you even find one of those combinations where the coefficients are not 0, this tells you that v1 is in the span of v2 and v3. So that means v1 is a linear combination of v1 and v3, and that's directly saying linearly dependent, right? That's the definition of dependent. They are in the span of each other, right? One of those vectors depends on the other vectors, right? So this is the test of linear independence. You put the vectors and you write this equation a1 v1 up to an vn, and you want all the coefficients to be 0. That's the only solution. There's no other solution. Now, if you are able to find v1 up to vk that are linearly independent in a vector space v, and the dimension of v is n, that means that k is less than or equal to n. Again, I've said this a few times, I'll say it again. What is the dimension? The dimension is the number of vectors in a basis. The dimension is how many, what's the maximum number of linearly independent vectors could we have in that space? The dimension, this is the number of vectors in a basis, which is very, very importantly the maximum number of linearly independent vectors in V. So you cannot have more than n linearly independent vectors in V. So if you have a set of linearly independent vectors, their number has to be less than or equal to the dimension. Right? So let's say, let me give you a quick example of this. So let's say the set 1, 2, 5, 6, 3, 3. Is this set linearly independent? And the answer is no, of course not. It's a red no. Why is it no? Because these vectors are in R2, right? These are 3 vectors in R2. How do I know that they are in R2? Because they have 2 components. So what's the dimension of R2? The dimension of R2 is 2. So I can have a maximum of 2 linearly independent vectors in R2. There's 3 here, so definitely these are dependent vectors. Right? Now, for 2 vectors only, this is a note that we mentioned in the midterm 2 session. I hope that you remember it if you were there. For 2 vectors, it's very simple to check linear independence. So if they are parallel, that means they are dependent. If they are not parallel, that means they are independent. 2 vectors is a very simple matter. If they're parallel, they're dependent. If they're not parallel, they're independent. Now, parallel just means that one of them is a multiple of the other. Right? So one of them is a multiple of the other. And really that's the idea behind linear independence. the heart of the matter and the one that gets asked the most is this idea that the only solution to this equation is the trivial solution where all the constants are equal to 0. Okay, what do we call a basis for a vector space V? So a basis for a vector space V, that would be a set of vectors V1 up to Vk is a basis for V. That tells you that V1 up to Vk is a generating set, and V1 to Vk is linearly independent. Now, because it's a generating set, that means k is bigger than or equal to n. So let's say this is the dimension of V is n. Because they're linearly independent, k is less than or equal to n, which tells you that basically k is equal to n. So, how many vectors are there in a basis? How many vectors are there in a basis? That's the dimension of the space n. So what's a basis? It's a set of vectors that are a generating set for the space and is linearly independent. And how many vectors are there in a basis? The dimension of the space. One more time, the dimension is the number of vectors in a basis, which is the maximum number of linearly independent vectors. Fair enough? So a basis is a set of vectors that generate the space, is a generating set for the space, and is linearly independent. Now, a couple of notes before we go back to the problems. Let's say somebody tells you that, let's say, vector space A or subspace H is the span of, let's say, V1 and V2. Right? Then automatically V1 and V2 would be a generating set for H. I feel a little silly saying this, but we get that, right? So H is the span of V1 and V2. H is all the linear combinations of V1 and V2. So V1 and V2 generate H, right? Any vector in H is a linear combination of V1 and V2. That's sort of the definition of generating set. Now, if V1 and V2 are linearly independent, so if is a linearly independent set, that tells you both of them. That means V1 and V2 form a basis. V1 for V2 is a basis. Right? So that's how we're going to find bases in some of the questions that they ask us. We're going to show that they are a generating set, and then we're going to show that they are linearly independent. Right? So that's sort of a couple of general notions that we really needed to know. This part is very, very important. Understanding this is very important, that for a generating set you need at least n, and for linearly independent you have at most n, where n is the dimension of the space. So next, let's do some practice problems. So let's continue. I was going to solve a problem from the 2017 final, but then I realized it needed some linear transformation knowledge, so I figured, you know, why not define also linear transformations, so we have all the definitions with us, and then going forward we can practice even more problems. So what's a linear transformation? A linear transformation is basically a function on vectors, right? A linear transformation is a function. So let's say T is a linear transformation that takes me from a vector space V to a vector space W, where T of a vector V in V gives me a vector W in W. and we know that t is linear, meaning that it has some very, very important properties. The transformation of a vector v1 plus vector v2 is the transformation of vector v1 plus the transformation of vector v2. So the transformation of a sum is the sum of the transformation, and the transformation of a constant times vector v is the constant times the transformation of vector v. So for example, if you were writing the transformation of a1 v1 plus a2 v2 plus, let's say, an vn, if t is linear, then you can easily write it as a1 the transformation of v1 plus a2 the transformation of v2 all the way till you get an the transformation of vn. Right? So if it's a linear transformation, that means it must satisfy the transformation of a sum is the sum of the transformation, and the transformation of a scalar multiplication is the scalar multiplication times is the scalar times the transformation of v. Now, linear transformation. Sorry, I was going to say this the other way around. Matrix transformations are linear transformations, but I will discuss matrix transformations a little bit later. We don't really need them for now, for the problems that would come now. So we're going to define, matrix transformations a little bit later. Actually, you know what, let's just define it right now and be done with it. So what do we call a matrix transformation? Sorry about that. If we leave it till later, it might get messy. So what's a matrix transformation? So it's a transformation that goes from a vector space V to a vector space W, where the transformation of V is described by a matrix of A times the vector V, which gives you the vector W. So this would be a matrix that induces T, so the matrix that represents T. So we say usually that A represents T, or A induces T, or A describes T. So whichever way you want, you can do it. Now, a matrix transformation, very important. A matrix transformation is 100% linear. So if you have a matrix transformation, you are guaranteed that it's a linear transformation. Now, very important note about linear transformation. So if T is a linear transformation, that tells you that the transformation of vector 0 is the vector 0. Now, it does not work the other way around. If the transformation of 0 is 0, that doesn't tell you that it's a linear transformation, right? But if it's a linear transformation, then T of 0 is 0. If you want to go backwards, you can say if T of 0 isn't 0, then T is not a linear transformation, right? So if it's linear, then T of 0 is 0. If T of 0 isn't 0, then it can't possibly be linear. I want to define two more entities that are very, very important, and they get asked all the time. What is the kernel? So the kernel of a linear transformation T. So let's define it properly. So let's say we have T, a transformation from V to W. The kernel of T is the set of vectors, all the vectors V in V, such that the transformation of V takes us to the 0 vector in W. So it's all the vectors where the transformation of those vectors gives us 0. Kernel is known to be a subspace of V. Now the image of T is all the vectors W in W such that there is V in V with transformation of V is equal to W. It's all the vectors in W that we get by transforming vectors in V. So it's a vector in W. If it comes from transforming a vector in V, then it's in the image. If not, then it's not in the image. And this is known to be a subspace of W. So the image is a subspace of W. Some other notions. We know that some notions are theorems, or if you want, we know that if the kernel of a transformation is just the 0 vector, because the 0 vector for sure belongs to the kernel, right? The transformation, if T is linear, the transformation of 0 is 0. So let's make this linear, because that's the only type of transformations we work with here. So 0 belongs to the kernel because the transformation of 0 is 0. So that's a vector that's guaranteed in the kernel. Now, if the kernel is only the 0 vector and there's no other vectors in the 0 vectors in the kernel, that means we call T is injective. Meaning, this works both ways. It means if V1 is different than V2, that tells you that the transformation of V1 is different from the transformation of V2. So no two vectors will go to the same image, and no two images come from the same vector. Right? That's basically it. Now, a very, very important theorem. I'm even going to write it in red, and this gets used a lot. The dimension of the kernel plus the dimension of the image is equal to the dimension of V. So the dimension of the kernel plus the dimension of the image is equal to the dimension of V, and that's a very important theorem. Right, so there's a lot more to work with here, but I just wanted to define some of the terms, some of the concepts that we're going to work with. Obviously, you've seen those definitions in the midterm 1 session and in the midterm 2 session, so these are things that supposedly you know. I just wanted to go over them really quickly before I start doing problems that need these notions, you know, so we go in a proper order kind of thing. So I define something, then I use it. Right, so now I promise we're going to go to the problems, and the first problem is this one. Okay, so let's look at this problem from 2017. The first part is a little bit standard. The second part, I put a pepper next to it, meaning it's a slightly difficult question. I mean, the first time you see it, but then once I show you how to do it, it should be easy. So, we have a vector space V and a vector space W. We have a linear mapping, meaning a linear transformation. How do we show that the kernel of L is a subspace of V, which is what I told you before. So, kernel of L is all the vectors in V such that the transformation L of V is equal to the 0 vector in W. Right? So, let's check that this is a linear mapping. First of all, the transformation, let's show that this is a subspace. the transformation of the vector 0 in V, that's the vector 0 in W. You know what, I'm not going to put arrows, we know those. So therefore 0, the vector 0 belongs to the kernel. Now, second condition, is it closed under addition? So let's take a vector v1 belong to the kernel of L, and let's take v2 belongs to the kernel of L. Okay, what does it mean that they belong to the kernel? That means the transformation of v1 is 0 and the transformation of v2 is 0. So what's the trend? Does v1 and v2 belong to the kernel? So the question is, does v1 plus v2, are they in the kernel of L? Now, they're in the kernel if their transformation is 0. So what's the transformation of v1 plus v2? The fact that the transformation is linear means this is the transformation of v1 plus the transformation of v2, and that just is 0 in W plus 0 in W, and that's the 0 vector in W. So v1 and v2 belong to the kernel of L. It's closed under addition. So third condition, let's pick a vector v in the kernel of L. That means the transformation of v is equal to 0. Let's check the scalar multiplication of v. So what's the transformation of alpha v? Because L is linear, it's the transformation of alpha times the transformation of v, which is alpha times 0, which is 0 in W. So the transformation of alpha v also gave us 0, so alpha, the scalar multiple of v, also belongs to the kernel of L, and therefore kernel of L is a subspace of V. So that's a standard type of proof. The next part is a little bit interesting. Show that if the kernel is 0, then the dimension of V is less than or equal to the dimension of W. We're used to seeing if the kernel is 0, then it's injective. So that's a little bit different. So we're saying if the kernel of L is only made up of the 0 vector, of course the 0 vector in V, then the dimension of V is less than or equal to the dimension in W of W. Okay, here's how we're gonna do this. So we're gonna say let the dimension of V equal to n. That means and let V1 up to Vn be, let's say, a basis of V. There's n the dimension of V is n, so a basis of V would have n factors. Of course, being a basis means they are linearly independent, and that's the fact that I want to use. So they are linearly independent. So that means A1 V1 plus A2 V2 plus dot 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 AN Vn equals to 0 has only the solution A1 equals to A1 equals to 0 all the way up till AN equals to 0. Now here's what I'm gonna try and show. I'm gonna show that the transformation LV1 and LV2 and LV3, all of those transformations are also linearly independent. So what is A So let's do B1 times LV1 plus B2 times the transformation of V2 plus dot 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 times Bn, the transformation of Vn equals to 0. So now, if we're solving this, if we solve B LV1 plus B2 LV2 plus all the way till Bn LVn, we can write this as the transformation of B1 V1 plus the transfer plus B2 V2 plus Bn Vn is equal to 0, right? Because this is a linear transformation. The transformation of a sum is the sum of the transformation, and so on, right? So this implies this. Now, the transformation of this is equal to 0 because the kernel only contains the 0 vector. Because the kernel, so this is the key point here, because the kernel of L is only the 0 vector, so whatever we send to 0 can only be the 0 vector. Therefore, B1 V1 plus all the way till Bn Vn must be the 0 vector in V, right? Because we took that vector and its transformation is 0. Now the only vector whose transformation is 0 is the 0 vector. The kernel of L is only the 0 vector. And we know that anytime you have an equation B1 V1 up to Bn Vn equals to 0, it only has the solution constants equal to 0. And therefore we get that B1 is equal to 0, B2 is equal to 0, all the way till Bn is equal to 0, which tells you that the transformations LV1 up to LVn is a linearly independent set. So this is a linearly independent set in W. Right, because the transformations are in W. So if this is a linearly independent set in W, so what does that mean? That means n, the number of those vectors, is less than or equal to the dimension of W. Remember what we talked when we talked about linear independence. I don't know why I have a blank page in here. So let's kill it. So remember when we talked about linear independence? So if these vectors are linearly independent in a subspace of dimension n, then the number of the vectors has to be less than the dimension. So here, these vectors are linearly independent in this, so the number of the vectors is less than or equal to the dimension of W. And what's n? N is the dimension of V. And isn't this what they want us to prove? It's a bit non-trivial, and I found it a little bit maybe difficult for the students, but you're very, very capable and you're totally able to do this. I don't know what happened to my screen. Well, so we're going to end the recording and I will solve a different problem. So let's continue with the practice. Sorry, at the end of the previous problem I lost focus for a second. My screen went black, so I wasn't able to see anything. I was saying the problem is difficult, but you know, now you've seen the solution and hopefully you understand the solution. So if it ever shows up again, I'm confident that you'll be able to do it. So this is a problem from a previous midterm, because there's not a lot of those types of questions on past finals, so I needed to do one. And I wanted to do an example of subspaces and linear independence and whatnot with a type of problem that doesn't have the usual addition and scalar multiplication. So we have a vector space. Let's call the vector space whatever, V. So I have the sum of vectors is defined in this particular way. and the scalar multiplication is defined in this way. You are told that this is a vector space, so you don't have to worry about this. So let's go through the parts of this problem. So for part A, we want to do this operation. So I'll copy them here, one by one, and then we will solve them. So this is part A. Of course, let's copy this, and whoops, I thought I copied it. So let's copy the definition of sum, and let's copy the definition of scalar multiplication so we can apply it here. So how do we do this operation? So the scalar multiplication, 5 times this, that's going to be 5 times x plus 5 minus 1, then 5 times y plus 2 times 5 minus 2, plus, now 3 times 2 plus 3 minus 1, and 3 times 1 plus 2 times 3 minus 2. So this is 10 plus 4 is 14, minus 15, so minus 5 minus 2 is minus 7. This is 6 plus 2 is 8. 9 minus 2 is 7. Then the addition is you take x1, you add it to x2, and you add 1. And you take y1, you add it to y2, and you just add 2. So this is 23 and 2. Straightforward. We've done a lot of these in the midterm 1 session. I hope that you could review those. Let's determine the 0 vector of this vector space. So there are many ways that we could determine the 0 vector. One way, we can do 0 times any vector AB. That should give us the 0 vector of the space, whatever V. Right? That's one way of doing it. I'm going to do it in 2 ways. So the first way is to do 0 times AB. So what is 0 times AB? We're doing this here. So that would be 0 times A plus 0 minus 1, 0 times B plus 2 times 0 minus 2. So that gives us the vector minus 1 minus 2. This is the 0 vector of this vector space V. The other way of finding the 0 vector is using the property of the 0 vector, which says that if AB is the 0 vector, so if AB is the 0 vector, then AB added to any vector xy should give us the vector xy. It shouldn't affect, like when you add it to a different vector, it shouldn't affect the other vector. So how do you add this? This is A plus x plus 1, B plus y plus 2. That is supposed to be xy. Remember, we are solving for AB. So A plus x plus 1 equals to x. Therefore, A is minus 1. And B plus y plus 2 is y. Therefore, B is minus 2. So you get the 0 vector minus 1 minus 2, which is the same thing as you got there. Good. Let's go to part C. Let B determine whether S is linearly independent or not. I love this. So here we have linear independence. We have 2 vectors, 1, 2, and 2, 4. Are they linearly independent? And my guess is that they are, because 1, 2, and 2, 4 are clearly not independent. They're dependent with the usual operations. So I'm guessing here that it's a trick for us to say that they are dependent, but in reality they are independent. Again, I don't know, but that's my feeling. So how do we check if they're linearly independent? So A times V1 plus B times V2 equals the zero vector. Don't forget that this is the zero vector. And if A equals to 0 and B equals to 0 only, then they're independent. So if A equals to 0 and B equals to 0 only, that means they are linearly independent. And if we have other solutions, then they're linearly dependent. And for better English, let's just put the only before. So if only A equals to 0 and B equals 0, that's the only solution, then they're linearly independent. Okay, so what's A times 1, 2 plus B times 2, 4 is equal to minus 1 minus 2. Now, what is scalar multiplication? Again, just allow me to copy these. So scalar multiplication, that's going to give me A times 1 plus A minus 1, then A times 2 plus 2 alpha, 2A minus 2, okay, plus B times 2 plus B minus 1, B times Y plus 2 times B minus 2. And this is supposed to be equal to minus 1 minus 2. So let's see, this is 2A minus 1, 4A minus 2, plus 3B minus 1, 6B minus 2. That's supposed to be minus 1 minus 2. So to add vectors, we do x1 plus x2 minus plus 1, and then 4A minus 2 plus 6B minus 2 plus 2. That's supposed to be minus 1 minus 2. So that gives me 2A plus 3B minus 2, sorry, minus 1 is supposed to be equal to minus 1, and 4A plus 6B, oh, I lost my hope, plus 2, minus 2 is equal to minus 2. No, they are dependent. So this leads to the system A plus 3B equals to 0. Oh, no, 2A plus 3B, oh yeah. And 4A plus 6B equals to 0. Both equations tell us that A is equal to minus 3B over 2. So if B, let's say, equals to 2, then A is equal to minus 3. So we A is equal to 0, B equals to 0 are not the only solution. Therefore, they are linearly dependent. I really thought that they would be independent. I want to check the solution, really. If you give me just a second, I would like to check the solution, see if I've done something wrong. What problem was that? Problem 3. Okay. Yeah, I got the wrong midterm. This isn't 2020 midterm 1, by the way. I was wrong, because I looked at 2020 midterm 1, and that is not it. Anyway, well, check my work. Was it maybe 2022 or 2021? Nope. Bizarre, I really thought this was 2020. Yeah, none of those are. So I'm not sure where this problem, it's from a midterm, I just can't seem to find the actual midterm I found. Anyway, so we discovered that they are linearly dependent. It's not the end of the world. Just double check all my calculations to make sure I didn't do a mistake. So let's do part D. Determine whether this is a subspace or this is not a subspace. So let's see. Is this a subspace or is this not a subspace of this space? So let's not forget that the zero vector is -1, -2, right? So this is the zero vector in V, or whatever, I call it V. So does it belong to S? So X is equal to Y plus 1. So this belongs to S. Okay, condition 1, check. Let's get two other, so let's get V1 in S. So actually let's not use V1, let's use X1, Y1. So X1, Y1 belong to S. That means X1 is equal to Y1 plus 1. And let's do X2, Y2 belongs to S. That means X2 is Y2 plus 1. Now we want to check if their sum belongs to S. So let's take this X1, Y1 plus X2, Y2. Now what's the definition of the sum? For the x's we add 1, for the y's we add 2. So X1 plus X2 plus 1, Y1 plus Y2 plus 2. Does it belong to S? So what is X1 plus X2 plus 1? X1 is Y1 plus 1, X2 is Y2 plus 1, and then we have 1, which is equal to Y1 plus Y2 plus 2 plus 1. So the X component, this is the X component, equals to the Y component plus 1. The X component equals to the Y component plus 1. So yes, it does. Now let's check scalar multiplication. So if I have xy belongs to S, which means that x is equal to y plus 1, alpha times xy, does it belong to S? So what is alpha xy? Let's copy this, put it here so we can write what alpha xy is, and let's create a blank page of buffer zone. So alpha xy is alpha x plus alpha minus 1, and then alpha y plus 2 alpha minus 2. Does this belong to S? Meaning, what is alpha x plus alpha minus 1? Now this is alpha, x is y plus 1 plus alpha minus 1. So this is alpha y plus alpha minus 1. So this is alpha y plus 2 alpha minus 1. Look at that. So you can write this as so I'm going to write it here. So you can write this as alpha y plus 2 alpha minus 2 plus 1. Right? The minus 1, write it as minus 2 plus 1. So this is the x component, which equals to the y component plus 1. So yes, it does belong to S. So S is a subspace of V. That's nice. Okay, let's look at part E, which is another check for a subspace. Now this one will be fast, you'll see it right away. Is this a subspace? It's all the points where x is equal to y. So the zero vector in V, which is -1, -2, does not belong to T, because x is not equal to y. Therefore, T is not a subspace. Right, so that was a quick subspace question. Right, so we've covered subspaces, we've covered linear independence, we have covered like the definition of dimension. Next, I want to go over systems of linear equations and RREF. Of course, that's not the end of the practice for subspaces. These are the problems that I am planning on doing. I will do some more subspaces, but let me first go over the topic one by one, and then at the end I will do extra practice from all the topics. So let's talk now about systems of linear equations, how we solve them briefly, and what is RREF, reduced row echelon form. So for example, I'm just going to copy a system for example. Let's say we are given this system of linear equations. Again, the topic here is systems of linear equations, reducing to reduced row echelon form, and writing the solution. So let's say, for example, you are given this system. How would you solve something like this? The idea is, first you form the augmented matrix. So you would get the matrix that contains the numbers, and then 2, -1, -7, and then 9, and then 1, 2, 4, and 2. And you want to reduce this matrix. Now, to reduce this matrix, the operations that we are allowed to use, which are called the elementary row operations, I refer to them as EROs, elementary row operations. We are allowed to switch two rows, so we're allowed to take row I switched with row J. We're allowed to multiply a row by a non-zero constant, and we are allowed to add a multiple of a row to another, so k row I plus row J into row J. Now, the way to reduce a matrix to RREF, first of all, what is RREF? So RREF is reduced row echelon form. It's a form that we put a matrix in. First condition is all zero rows. Of course, if any, you may not have zero rows. Our zero rows, if any, are at the bottom. The first non-zero entry of every non-zero row is a 1. This is what we call the leading one. So if we have a row that's not entirely zeros, the first entry that's not zero in a row must be a 1, which we call the leading one. Leading ones go left to right, so leading ones should go like this. We can't have leading ones just like just moving around. We can't have a leading one, you know, here and then here and then here and then here. They have to go left to right. There's no two leading ones on top of each other either. And the fourth condition is above. And of course, and below, but the below we have it from before. All leading ones are zeros. So above and below all leading ones are zeros. If you only have this, then this is called REF, row echelon form. So if it's only below the leading ones that are zeros, then that's REF. If it's below and above all leading ones are zeros, then that's reduced row echelon form. Now, how do we achieve row echelon form? Some people do it randomly. They just move things around, simplify whatever and get there. But there's a better way to do it. It's a strategy. I prefer if you use the strategy because it gets you there like consistently every time. So we work column by column, meaning I finish working in my first column, then I move to my second column, then my third column, and so on. In a column, we first get the 1. So we first get the leading one in every column, and then we use the 1 to get the zeros. So I'm going to apply this to this problem. We want to solve this system. So in my first column, I'm going to start working in the first column. I need a 1 over here, which I have it. So I'm going to use that 1 to get a 0 over here and a 0 over here. So I'm going to do the operations. Minus 2 times row 1 added to row 2. That's my new row 2. That's the row that will change. And minus row 1 plus row 3 into row 3. That's my new row 3. So that'll give me 1, 3, 7, 1. Now minus 2 this plus this, 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 and then minus this plus this, minus this plus this, minus this plus this, and minus this plus this. I finished working in my column 1. I go to column 2. In column 2, here is where I need the 1 to be. So I'm going to take row 2, I'm going to divide it by minus 7, and then I'm going to put the result in row 2. So that'll give me 1, 3, 7, 1, 0, 1, 3, minus 1, 0, minus 1, minus 3, 1. I got the 1 where I need it to be. I'm going to use it to get zeros here and zeros here because my aim is RREF. So minus 3 times row 2 added to row 1. And minus, not minus, just row 2 added to row 3. That's my new row 3. Notice how we always add to the row we're changing. We add to the row that we're changing. We don't minus from the row we're changing. So this is going to give me the last row. You can see that it just cancels out. It's a bunch of zeros. And this is 0, 1, 3, minus 1. So minus 3 this plus this, minus 3 this plus this, minus 3 this plus this. And ladies and gentlemen, this matrix is RREF. So this is a matrix that is in RREF. All the 0 rows at the bottom. The first non-zero entry of every non-zero row is a 1. So 1, 1. Above and below all leading ones, we have zeros. Now there's no leading 1 in column 3, so there would be no zeros. Now, how would I solve this matrix? How would I write my solution? This is the column for X, this is the column for Y, and this is the column for Z. So, the variables that do not have a leading 1, they're called free variables. Those get the parameter. So, Z doesn't have a leading 1, so Z gets a parameter, meaning Z is a free variable. Basically means it could be whatever it wants. So, from this row, from here, we know that Y plus 3Z is minus 1. So Y is minus 1, move this to the other side, minus 3Z, so minus 3T. And X is equal to 4 plus 2T. So this is the solution for any t, which means we have infinitely many solutions. Of course, anytime we have a free variable, automatically we have infinitely many solutions. Now we can write it like this, or sometimes they ask us to write it in vector form. So it's constants plus coefficients of t. Of course, that's x, y, z. So x is equal to 4 plus 2t, y equals to minus 1 minus 3t, and z is 0 plus 1t. Right? So that's one way to, I mean, that's one way, that's the way to solve this system. So if I look at the question that they asked in 2019, I basically solved them for you. So I reduced this matrix, I parametrized all solutions to this, so this is done. Now there's only part C that we haven't done. So right, so this is part A, so you can just picture the matrix without this. Then we used, so okay, let me just show you. So to reduce this, we have done this already, right? So this is everything that we have here. Or is it? 1371, 1371, 2 minus 1 minus 7, 9. Yeah, this is it. So this is the same matrix. So we reduced it, we solved the system. The only thing left is part C to find H1 such that it's equal to this. So basically, what are we finding? Look, this is 1 alpha 1. We're solving the system. And let's go back to this problem. This is what they asked on the final of 2019. First, they asked you to reduce this matrix, which we did. Then they asked you to solve the system, which is basically writing it as this matrix and then solving. So I remind you what we got as a final answer. We got this. So now what they're asking us to solve is this. So look at this. This is saying 1 alpha 1 plus 3 alpha 2 plus 7 alpha 3 is 1. Are you seeing this? 2 alpha 1 minus alpha 2 minus 7 alpha 3 is 9. Same thing as row 2. And then alpha 1 plus 2 alpha 2 plus 4 alpha 3 is 2. So that's basically the system. Right? So it means that the alphas are the same thing as the x1, x2, x3. So it means that the alphas are basically what we got for x1, x2, x3. So this is alpha 1, this is alpha 2, and this is alpha 3. And you pick whatever value of t you want. So if they want you to find alpha 1, alpha 2, and alpha 3, say for t is equal to 1, alpha 1 is equal to 6, alpha 2 is equal to minus 4, and alpha 3 is 1. Of course, you could have picked any t, but this entire problem was basically solving a system of linear equations. Okay, can we try maybe solving this one? So 2, 1, 3, 4, 1, 0, 1, 1, 0, 2, 3, 8. So maybe you want to pause right now and then try it on your own and then come back and check the answers. Now, I'm working in the first column, so I'm going to switch those two rows to get the 1 there. There's no need to divide by 2 and get fractions. So this is 1, 0, 1, 1. 2, 1, 3, 4, 0, 2, 3, 8. Now, I got the one where I need it to be. I need a 0 here. So the operation is minus 2 row 1 added to row 2. That's my new row 2. So this is 1, 0, 1, 1. Minus 2 this plus this, 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 and then 0, 2, 3, 8. Finished working in my first column. In my second column, I got the one where I need it to be. I need to get a 0 over here. So I'll continue on this side. So I'm going to do minus 2 row 2 added to row 3 into row 3. That'll give me 1, 0, 1, 1. 0, 1, 1, 2. So minus 2 this plus this, minus 2 this plus this, minus 2 this plus this, minus 2 this plus this. Finished working in the second column. Now for the third column, I have the one where I need it to be. So I'm going to use it to get 0s here and 0s here. So minus row 3 added to row 2, that's my new row 2. And minus row 3 plus row 1 into row 1, that's my new row 1. So this is the final matrix. 0, 0, 1, 4. Minus this plus this, minus this plus this, minus this plus this. Here we go. So x is equal to minus 3, y equals to minus 2, z is equal to 4. And this is what we call a unique solution. There's no parameter, so it's a unique solution. Right, let's continue with some practice. This is what they asked in 2018. I like this problem. So it's a little bit more different than the usual. 2017 also they asked a similar one. So I'm going to take a short break and then I'm going to come back to solve this. Of course, you won't feel anything in the videos. They'll just continue. But I'm just letting you know. So this is what they asked in 2018, I'm sorry, about systems of linear equations. So write the augmented matrix, that's no problem. 1, 1, 2, 1, and then 1. x1, 2x2, 3x3, no x4, and then 4. And then ax1, ax2, 2ax3, and 1x4 equals to 5. So transformed the matrix into row echelon form. So we don't need above and below, we just need the below, the leading ones. So we have the leading one where we need it. So we're going to get a 0 over here and a 0 over here. So minus row 1 added to row 2, that's my new row 2. Minus a row 1 plus row 3 into row 3, that's my new row 3. So this gives me 1, 1, 2, 1, 1. Minus this plus this, minus this plus this, minus this plus this, minus this plus this, and minus this plus this. Minus a row 1 plus row 3, 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 minus a row 1 plus row 3. And ladies and gentlemen, that is REF. We have a leading one here. We have a leading one here. We don't have a leading one in the third column, but that's potentially a leading one in row 4, in column 4. Okay, so that would be part B. For part C, determine all the values of A for which the system has no solution. So if we want the system to have a no solution, what we want is to have 0, 0, 0, 0, and then number. That's not equal to 0. Because that way we would say 0x plus 0y plus 0z plus 0w equals to 5, and that's not possible, right? So that means we want 1 minus a to be 0 and 5 minus a to be not 0. Well, if you solve this, then this is basically a equals to 1. So if a equals to 1, then this system would have, then 1 minus a would be 0, and 5 minus a would be 4, so you would get no solution. Right, so the last line would be 0, 0, 0, 0, 4, and that tells you that this system has no solution because 0x plus 0y can't equal to 4, right? Now, they're saying in part D, let a equals to 5. So we're going to rewrite all of this and make a equals to 5. So 1 minus a is minus 4, and that's 0. So we're going to solve it using back substitution, they're asking. So let's do that. This row tells me that minus 4w equals to 0. So w is equal to 0. This row tells me that y plus z minus w equals to 3. Now w is 0, so y is equal to 3 minus z. And this row tells me that x plus y plus 2z plus w equals to 0. And you know what? I'm going to move this to a different location to be able to work with it. So that's row 1. So x is equal to minus y minus 2z, and I don't know why I said equals to 0, it's equal to 1, minus 2z minus w plus 1. Now y is 3 minus z, so minus 3 minus z minus 2z, w is 0 plus 1. So that would be minus 3 plus 1 is minus 2, plus z minus 2z, so minus z. Minus 3 plus 1, and then plus z minus 2z. So our solution is x is equal to minus 2 minus z, or if we let z is equal to t, then x is equal to minus 2 minus t, y is equal to 3 minus t, and w equals to 0 for any t. You could have kept x and y in terms of z, that's no problem. So that's an interesting question on the 2018 final. 2017 they asked the same. I think that's the last one I'm planning on solving with systems of linear equations. So let's do it. Write the augmented matrix, a similar problem. So for part A, they're asking us to write the augmented matrix 1, 2, 3, and then a plus 2, 3, 1, 8, 4a, 2, 4, 2, 3a plus 3, and then 1, 4b, 5a. How exciting. Transform the matrix into row echelon form. Great, so I got the one where I need it. I want to get zeros here, here, and here. So minus 2 minus 3 row 1 plus row 2 into row 2 minus 2 row 1 plus row 3 into row 3 and minus row 1 plus row 4 into row 4. So this will give us 1, 2, 3, a plus 2. So minus 3 this plus this, minus 3 this plus this, minus 3 this plus this, minus 3 this plus 4a, so a minus 6, minus 2 this plus this, 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 so a minus 1, minus this plus this, minus this plus this, minus this plus this, right? Yeah. And minus this plus this, so 4a minus 2. Let me check it again. 1, 2. See here, that's 1, 2, 1. See, I messed up. So 1, 2, 1, a plus 2. 3, 1, 8, 4a. 2, 4, 2, 3a plus 3. And 1, 4b, 5a. Okay, so that affects all of those numbers. So minus 3 this plus this, minus 3 this plus this, minus 3 this plus this, then minus 2 this plus this, minus 2 this plus this, minus 2 this plus this, and then minus this plus this, minus this plus this, minus this plus this, and minus this plus this. Great. So we want to move the row 3 down. So basically that should switch with that. So that'll give us 0, 2, b minus 1, 4a minus 2, 0, 0, 0, a minus 1. So now we would like to get a 1 over here. So let's take row 2 and divide it by minus 5. One, 2, 1, a plus 2. So 0, 1, minus 1, a minus 6 over 5. That's very strange that these values are so. Usually when they give a problem like this with constants a and b, it's much easier to simplify the system. Unless I made a mistake again, I'm going to check that I copied correctly. It seems okay. So okay, sorry, let me just verify it once again. I don't want to be doing all the work and then discover a mistake later. So 1, 2, 1, a plus 2, 3, 1, 8, 4a, 2, 4, 2, 3a plus 3, 1, 4b, 5a. So minus 3 this plus this, minus 3 this, so minus 6, minus 3 this plus this, minus 3 this, so minus 3a minus 6 plus 4a, so that would be a minus 6, correct? Then minus 2 this plus this, 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 so a minus 1, and then minus this plus this, minus this plus this, minus this plus this, so that would be 4a minus 2. Okay, so that's correct. Now switching those two rows, excellent. So if we want a solution, then a has to be equal to 1. So because of this row, to get any solution, a must equal to 1. So there's no chance that you would get a solution if a is not equal to 1. So that's how I'm gonna go with this. So to get a solution, you definitely have to get A equals to 1. So in part B, transform the matrix into row echelon form. So we're not at row echelon form yet, but to get any solution, we really have to have A equals to 1. We could, again, we could just take this and divide the row by 5. If I move this up, and then I can divide by 2. If you want, we can switch these two rows, and then dividing by 2 might be easier than dividing by -5. So we can take, it doesn't really matter, let's just divide by -5. Row 2 divided by -5 into row 2. So that's going to give us 1, 2, 1, A plus 2. Then 0, 1, minus 1. A over 5 minus, dividing by -5. So minus A over 5 plus 6 over 5. And then 0, 2, B minus 1. 4A minus 2. 0, 0, 0, A minus 1. So now to get it into REF, I just need to get this as a 0. So minus 2 row 2 plus row 3 into row 3. So 1, 2, 1, A plus 2, 0, 1, minus 1, minus A over 5 plus 6 over 5. So minus 2 this plus this, minus 2 this plus this, minus 2 this. So this is 2A over 5 minus 12 over 5 plus 4A minus 2. Again, it's very bizarre that the numbers are like this. Usually they make them nicer. So 4A, that's 22A over 5. Minus 14 over 5, and then 0, 0, 0, A minus 1. So I'm going to say that this is REF, even though those are not leading ones, but they're places for leading ones, so we're good. We go to part C. We want infinitely many solutions. Well, if you want any solutions at all, A has to be equal to 1. Right? If you want any solution at all, A has to be equal to 1. So if I make A equals to 1, that'll give me 0, 0, 0, 0. And then this is 0, 0, B plus 1. So 22 over 5 minus 14 over 5, that's 8 over 5. And then this is 0, 1, minus 1. That would be minus 1, that would be 1. And then 1, 2, 1, and that would be 3. So the problem is here, what's the value of B that would give me infinitely many solutions? It's impossible. So no B gives infinitely many solutions. So I mean, to get infinitely many solutions, we need this to be 0, right? And if this is 0, then this is equal to 8 over 5, which would be no solution. So I'm not sure if there was a typo in this problem. I'm not sure if they changed it somehow, but there is no A and B that would give us infinitely many solutions. I will check it on the break to see if I made it, like I'll stop and I'll check this to see if I've done any mistakes or anything, but I checked it a few times already with you right now, and we didn't come to a we didn't see anything that's a mistake. I'll check it again once I take a break before I go to another topic, and if I find any issues with it, then I will correct it. And if I don't find any issues, the next topic at hand will be linear transformations, and I don't know what happened with that semester. Maybe they corrected it, maybe they said something to the students during the exam. I'm not really sure. Hey guys, so I found the solution when I was reviewing this again. Minus 12 over 5 minus 2 is minus 22 over 5. So that was the mistake right here. So now when a is equal to 1, to get any type of solution, this would be 0. Right? And then to get infinitely many solutions, then if we have to take b equals to minus 1, then that would give us a 0 over here, and we're going to get infinitely many solutions. So let's continue with this. So there was a calculation mistake that made this 22 over 5, which makes all the difference, because now when I make a equals to 1, to make sure that I get a solution over here, that also gets this number to being 0, so we get this. So if we make b equals to minus 1, meaning this is also 0, that would give us the system 1, 2, 1, 3, 0, 1, minus 1, 1, and 0, 0, 0, 0, 0, 0, 0, 0. So it was my mistake. The calculations are a little bit harder than average, but I suspect they're not that bad. We just have to make sure that we don't make a mistake like I did. So if z is equal to a parameter t, then y is equal to 1 plus t by moving this to the other side, and then x is equal to 3 minus 2y minus z. So 3 minus 2 times 1 plus t minus z, which is t. So 3 minus 2 is 1, minus 2t minus t is minus 3t. Right, and that is the solution. So I'm guessing there, for those values, determine the set of all solutions using back substitutions, and that's it. So z is equal to t, y is equal to 1 plus t, and x is equal to 3 minus z minus 2y. We replace y by its value and we get this, and this is the solution for any t. So sorry about that typo, I didn't catch it earlier, but now we caught it, and we have two very nice solutions to the 2017 and 2018 systems of linear equations. Next is a new topic. Let's now discuss the idea of linear transformations. I did go over some of the theories, some of the small theory with you before, but now we're going to practice this. So let's, open, actually, yeah, let me, sorry, I'm just thinking of the space options, so I'm going to move this here, and then we could just solve it here. So this is the first problem we do with linear transformations. Suppose that L is a transformation from R2 to R3, and it's a linear transformation. By the way, as we said earlier, if it's a linear transformation, that means it must be a matrix transformation from R2 to R3. In fact, we said in the midterm session that the size of A would be 3 by 2. So the size of the matrix that induces this, the matrix that represents L, that would be 3 by 2. So A would be 3 by 2, which would be 3 rows and 2 columns. So A, B, or A, let's just do A, B, C, D, E, F, something like this. So we know that L of 5, 2 is 3, 2 minus 4, and L of 2, 1 is 1, 2 minus 1. There's two ways of doing this problem. You know that, actually maybe you don't know that, but it's a fact that the column 1 of A, that's the transformation of the vector 1, 0, and column 2 of A is the transformation of vector 0, 1. So the columns of the matrix that induces a transformation are the effect of the transformation on the standard basis. So the column 1 of this matrix is the effect of the transformation on 1, 0, and column 2 is the effect of the transformation on 0, 1, which happen to be the basis of R2, the standard basis of R2. So one way to do this problem is to write 1, 0 as a combination of 5, 2 and 2, 1, and then to write 0, 1 as a combination of 5, 2 and 2, 1. Then we'll be able to find the transformation of 1, 0 and 0, 1, and those are the columns. Or you could just do it like not do this way and say that if I have A, B, C, D, E, F times the vector 5, 2, that gives me 3, 2, minus 4, meaning that 5A plus 2D is 3, 5B plus 2E is 2, and then 5C plus 2F is minus 4. Now I have that A, B, C, D, E, F multiplied by 2, 1 is equal to 1, 2, minus 1. So this would mean 2A plus D equals to 1, 2B plus E equals to 2, and 2C plus F is equal to minus 1. So you can do this with this and solve for A and D. You can do this with this and solve for B and E. And then you can do this with this and solve for C and F. So I'm going to solve one of them and then the rest I'll leave up to you. So if we have 5A plus 2D equals to 3 and then 2A plus D equals to 1. You can solve however way you want. You can use matrices, you can use those high school methods you learned. Like if you call this equation 1 and you call this equation 2, you can do equation 1 minus twice equation 2, and you get rid of the d's in this way. So 5A minus 4A is A, 2D minus 2D is gone, 3 minus 2 is 1. Then you replace the A here and you're going to get D equals to minus 1. So that would be, if you solve the other systems, you're going to get B equals, E equals, C equals, F equals. So this minus 2, this is B, this minus 2, this minus 2, this. So B is minus 2. If B is minus 2, that's minus 10. So that's 12, E is 6. And then C, this minus 2, this minus 2, this minus 2, this, that's minus 2. And if C is minus 2, that's minus 4. You move it to the other side, it becomes 4, so F is 3. Of course, please check my work. So we're going to get that the matrix A that represents T is A, B, C, D, E, F. And for part B, if you want to do the transformation of the vector 4, 1, basically take this 1 minus 1, minus 2 minus 3, minus 1, sorry, minus 2 minus 3, minus 1, 6, 3, and we're multiplying it by the vector 4, 1. So that gives us 4 minus 1 is 3, minus 8 plus 6 is minus 2, minus 12 plus 3 is minus 9. And that's a simple exercise. It just has some labor to it. You gotta labor to find the solutions. By the way, now that we found A, we know that this is the transformation of the vector 1, 0, if you ever need it, and this is the transformation of the vector 0, 1. So we didn't really need to express 1, 0 and 0, 1. We just went by like simple calculations, and it's not as bad, right? So for something that's a little bit more theoretical, and this was asked on 2019, let's talk about this. State the rank nullity theorem. Very important. The rank nullity theorem is, we're going to talk about it later, but it says that the dimension of the kernel of L, I think I mentioned it, plus the dimension of the image of L is equal to n. It's the dimension of this, the dimension of V. By the way, this is what you call the rank. This is what's called rank. And this is what's called nullity. The dimension of the kernel is called nullity, and the dimension of the rank, dimension of the image is called rank. I remind you that kernel is a subspace of Rn, image is a subspace of Rn. State without proof what L surjective means. Surjective, it means it covers the entire Rm. It means the image of the transformation is the entire Rm. Surjective means the image of L is the entire Rm. That means the dimension of the image of L is equal to m. Surjective means the transformation covers all of the range. So the image is the whole Rm. What does it mean that L is injective? That means the dimension of the kernel of L is 0. It means the kernel of L is only the 0 vector. So the dimension of the kernel is 0. Great. Suppose we know that L is surjective, so we don't know that it is injective, we just know that it's surjective. State with proof which inequality must hold between n and m. So remember, n is the dimension of this space, m is the dimension of this space. So we know that the dimension of the kernel plus the dimension of the image is supposed to be n. When L is surjective, the dimension of the image is m. So the dimension of the kernel plus m is equal to n. And they're saying inequality. I mean, I'm not sure. If the dimension of the kernel of L is bigger than 0, because they're not telling us that it's injective, so the dimension of the kernel is bigger than 0, that means that m is less than n, right? Because then m would be n minus the dimension of the kernel. Also, m is bigger than L, sorry. So this is not a positive quantity, this is not a 0 quantity, this is something positive. So m must be bigger than n. If we don't know what the dimension of the kernel is, if this is not given, then we can say m is bigger than or equal to n. It's equal if the dimension of the kernel is 0. So the equal is when the dimension of the kernel of L is equal to 0. And if the dimension of the kernel is bigger than 0, then m is definitely bigger than n. Right? So some small reminders of topics involving linear transformations. And now we're gonna talk about how to find the basis for the kernel and the basis for the image space. So I'm gonna just write that down for you. So how do we find the basis for the image space of a transformation, which is the same thing as the image space of the matrix A that represents the transformation? So to find the basis for image of A, those are the columns of A, very important, the columns of A that ended up with a 1 once you do RREF. So you find out which columns ended up with a 1 in RREF and you pick those columns from A. By the way, how many of those columns are? So the dimension of the image space of A, that's equal to the number of vectors in a basis. So that means those are the number of columns that ended up with a 1 in RREF. So however many columns ended up with a 1 in RREF, that means this is the number of leading ones. So this is the number of leading ones, which means that's the rank of A. The definition of the number of leading ones in a matrix in RREF, the definition of the number of leading ones in RREF, that's called the rank. So that's why we call the dimension of the image of A the rank of A. And when you want to find a basis for the kernel of L, or the kernel of the matrix A, basically you're going to solve AX equals to 0. So what you do is you take A, you put a bunch of zeros on this side, then you reduce, you go to RREF, and then you're going to get a bunch of zeros. And by solving this, you get the basis for the kernel of L. I remind you that the kernel of L are all the vectors such that when we multiply A by them, we get 0. So here, we're solving AX equals to 0. So we're getting the solutions to this are going to form the basis for the kernel of L. So it's best to see all of this through an example, and the examples are right here. So I'm going to take a short break, and then obviously you'll feel anything again. It's a pre-recorded, and then I'll come back to solve this. Let's continue with the practice of finding the basis of the image and the basis of the kernel and working through those topics. This is the question that they've asked in 2021. Sorry, in 2020. This is a common question on finals. I've seen it asked several times. So I'm going to copy it to a new page and then we talk about it. So again, this is the final. It was the midterm 3 of 2020. In 2020 they didn't have a final. Wait, or it was the midterm 2 of 20. I forgot honestly if this was the final, the midterm 3 or the midterm 2, but this was from 2020, and it's a good practice for the image and the kernel. So here's a matrix A, and they gave us the RREF of A, so they saved us the time to reduce the matrix. Let L be the linear transformation whose standard matrix is A. Notice that the size of A is 4 rows, 5 columns, which is not surprising, 4 by 5. How do we find the basis for the image space of L? Remember, the image space of L, as a quick reminder, the image space of L, this is all the vectors V in, or let's call them W, in R4, such that there is V in R5, such that AV is equal to W. So all of those that we can get using the transformation, all of those that are the images of some vector V in R5. Another way that looking of the image space of L, that would be the span of the columns of A. Right. Another way of looking at the image of L, that would be the span of the columns of A. So any vector that belongs to the span of the columns. So any vector that's a linear combination of the columns. And this is why when we reduce to RREF, we look at the columns that have a leading one, and we say that those form the basis. Why do we look for the columns that have leading ones? Because we're looking for the columns that are linearly independent, right? And if these columns are the linearly independent columns, then these columns would be the basis of image L, because they clearly span. Other columns are combination of those columns, because the other columns didn't have a leading one. These are the columns that ended up with the leading one. So those three columns, column 1, column 2, and column 4, are the linearly independent columns that span the column space, or the column space or the image space, and therefore they form the basic. So 2, 0, 3, 5. Remember, we get the columns that have a leading one in RREF, but we pick up the column from the original matrix A. 0, 1, 2, 6, and the fourth column is 2, 3, 1, 5. Remember, a basis is not unique, so there could be other bases for this. And therefore, what is the dimension of the image space of L? That would be 3, because there are 3 vectors in the basis of the image space. So, is L surjective? Surjective means, remember, surjective means the image space of L equals the entire R4. Now, look at this and tell me, is this map surjective? Clearly not. Right? So this is not surjective. Why is that? Because while the image space, because the dimension of the image space of L is equal to 3, it's less than 4, which is the dimension of R4. Right? We know that the image space of L is a subspace of R4. So if you want it to be the entire R4, then it should be a subspace of R4 that has dimension 4, but it doesn't have dimension 4, it has dimension 3. Right? How do we find a basis for the kernel of L? So we're going to copy this matrix, and I'll remind you how we find the basis of the kernel. So to find the basis, a basis of the kernel, we're going to solve Ax equals to 0. This means we are looking for all vectors x such that the transformation of the vector x gives us 0. And that's basically the definition of the vectors in the kernel. Just give me a second. So when we want to solve Ax equals to 0, we're going to put A, we're going to put a bunch of zeros here, right? And then we're going to reduce. When you reduce, here they gave us the RREF. So all we're missing is just putting a bunch of zeros on this end. 4 zeros. Right? So basically you're just solving with these 4 zeros on this end. So this is why they give you the RREF, to make it very simple for you to solve all this without making any mistakes using the RREF. So how do we solve this? You remember how we solve systems. We practiced this already. We have 5 variables, so let's call them x1, x2, x3, x4. So x1 got a leading one, x2 got a leading one, x4 got a leading one. So x3 gets a parameter and x5 gets a parameter. So x5 is equal to t, x3 is equal to s. Now from this line we can get that x4 is 0 minus x5, so minus t. From the first line we get that x1, wait, I skipped the second line. From the second line we have x2 is equal to, move the minus 3 over, move the minus 4 over, so that would be 3s plus 4t, and then x1 is equal to minus 4s minus 3t. So this is the solution. This is all the vectors such that, all the forms of vectors such that if we multiply a by those vectors we get 0. So the vectors have the form something plus s plus something times t. So that would be minus 4s minus 3t, 3s 4t, 1s no t, 0s minus 1t, and 0s 1t. Right? So what's the basis for the kernel? Basically the kernel of L is created by those two vectors. Is the span of those two vectors. So a basis for the kernel will just be those two vectors. So this vector and this vector. So what is the dimension of the kernel? The dimension of the kernel is equal to 2 because there are two vectors in the basis. Now, I want to say a few things about this to solidify what we've learned before. What was the dimension of the image space? The dimension of the image space was those three columns. Why did we choose those three columns? Because there were three leading ones in RREF. 1, 2, 3. There were three leading ones in RREF. So the dimension of the kernel, the dimension of the image of L or the image of A, that's the same thing, is basically the number of leading ones in RREF, which we called it the rank, right? So we called it the rank of A. Great. What is the dimension of the kernel? The dimension of the kernel was 2. Why is it 2? Because we have two vectors in the basis. Why did we get two vectors in the basis? Because we have two parameters. We have the S and we have the T, right? We have two parameters. So the dimension of the kernel of L, which is the kernel of A, same thing, is the number of parameters. Now, how many parameters did we get? We get the number of parameters is n, the number of variables, which is, by the way, the dimension of Rn. Sorry, let's not use n in general. Let's use what it is here. It's 5. So you had 5 variables, right? 5 variables. So this would be the number of variables, which is basically the dimension of R5 minus however many variables had leading ones. So the number of parameters are the variables that don't have a leading one. So how many variables you have minus the number of leading ones. So minus the number of leading ones, which we called it the rank, which is the dimension of the image space of L, right? Now move the image space of L. So what we just got is that the dimension of the kernel, move the dimension to the other side, plus the dimension of the image is equal to the dimension of R5. Isn't this the rank nullity theorem? This is called the nullity. This we called it the rank. And this is the dimension of V or Rn. Right? If the transformation L goes from V to W. So that's why the rank nullity theorem works, because the dimension of the image space is the number of leading ones, and the dimension of the kernel is however many variables minus however many leading ones you got, and the number of variables is the dimension of the space that you start with, which is the dimension of R5 in this case. Right? I hope that puts this into more light and you can actually see it better. Is L injective? Well, we talked about this. L is injective. That means we should have the kernel of L only contain the zero vector. That's what means L to be injective. So the kernel of L is only the zero vector. And in this case, it isn't. So no, it isn't. It isn't injective because the kernel is clearly not only the zero vector. The kernel has dimension 2. If the kernel is only the zero vector, that means the dimension of the kernel of L would be 0. State the rank nullity theorem and verify the rank nullity theorem. Well, We explored it, we explained it, we did a lot of work on it. I hope that makes it more clear. Let's continue with the same idea. So this is the same problem. Notice they also asked the same type on 2019. So let's do this very quickly. What's the dimension of the basis? Well, we go to our REF, column 1, column 2, and column 4 got leading ones. That looks like exactly the same question that we had before. Well, almost. It's almost identical to the one in 2020, which gives us hope, right? If the problems are all coming the same, then maybe your final has also problems that look like this. So so the basis of the image space is gonna be first column, second column, and then fourth column. What is the dimension of the image space of L? The dimension of the image space of L, which is, by the way, the same idea as the image space of A. That's 3, because we have 3 vectors in the basis, or 3 leading ones. A basis for the kernel, so I'm going to copy this. You know what? I'm going to be... So here's the RREF. We're solving AX equals to 0. This is very similar to the last one. By the way, without solving for the basis of the kernel, what's the dimension of the kernel of L? Well, we have 5 variables, and the rank is 3, so that would be 2. So this is N, and this is the dimension of the image of L. Right, so we know that we're expecting 2 parameters. We know that the dimension of the kernel will be 2. So let's solve for it really quickly. x1 got a leading 1, x2 got a leading 1, x4 got a leading 1. So x5 is t, x3 is s, so x4 is minus 2t. We're solving from this line. From this line we have x2 is equal to minus 2s plus t, and from this line we have x1 is equal to 3s minus 2t. So we're gonna get one vector for t, one vector for s, and those would be the basis, or a basis for the kernel. So 3s minus, s and t, that's 3s minus 2t minus 2s 1t, 1s no t, 0s minus 2t, 0s 1t. So a basis for the kernel space of L is equal to the vectors 3 minus 2 1 0 0 minus 2 1 0 minus 2 1. And as expected, the dimension of the kernel is 2. Alright? Same story. So find the basis for the kernel, compute the dimension of the kernel, find a basis for the image space, compute the dimension, and verify the rank nullity theorem. Again, very similar to what we just did. So all you need to do is find the RREF of A. So I'll give you the answer to this. So what is the RREF of A? Well, you know what? Let's practice one more time reducing this matrix. It won't hurt us to practice it one more time in details, but you know, last time. So I got the leading one where I need it. So I'm gonna do, I need zeros here and here. So minus 3 row 1 plus row 2 into row 2, and 2 row 1 plus row 3 into row 3. That gives us So 1, 1, 2, minus 1, minus 3 this plus this, 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 2 this plus this, 2 this plus this, 2 this plus this, and 2 this plus this. Well, you see right away that if I take row 2 divided by minus 3 and I put it in row 2, that'll give me 1, 1, 2, minus 1, 0, 1, 0, 0, 0, 1, 0, 2, 0, 0. And now I can cancel this and cancel this. So minus row 2 plus row 1 into row 1, and minus 2 row 2 plus row 3 into row 3. That basically gives us this, where we have 0 here and 0 here. So column 1 has a leading 1, column 2 has a leading 1. So if we want a basis, so I'll put the answers on this side. So let's first solve for the kernel. So for the kernel, we have to pretend that there is 0, 0, 0 here, and we're solving the system. So for the kernel of L, x1 got a leading 1, x2 got a leading 1, x3 didn't, so x3 is t, x4 is s. Now from this line we're gonna get minus 2t minus plus s, that's x1, and x2 is basically equal to 0. Look, this line tells me that x2 is 0. So x1 is equal to minus 2t plus s. So 1 column for t, 1 column for s, 2t, 1s, zeros, 1t, no s, no t, 1s. So a basis for the kernel of L is 2, 0, 1, 0, 1, 0, 0, 1. The dimension of the kernel of L is equal to 2. So if you want to find the image space of L, column 1 and column 2 are the ones that turned out with leading ones. So a basis would be the column 1 and column 2. And we knew this already, but the dimension of the image of L is 2. And of course, the dimension of the kernel is 2, the dimension of the image is 2, and n is 4, right? N is 4. Remember, if it's a 3 by 4 matrix, it means the transformation is 3 by 4, right? You read it 3 by 4. So n is 4. N is the dimension of the space that we start with. Verify 2 plus 2 is equal to 4. That's just simple. Right, so that's more practice about the image space and the kernel and all that. So now I'm gonna do more practice. I wanted to do more practice for span, linear independence, basis, and dimension, and we're gonna do just that. Let's now practice some questions about spanning, linear independence, and all that. This was a question in 2018, and I thought this was an interesting question, so let's put it here. So this is again from the final of 2018. The 2018 had a final, and this is very theoretical. I like it because it gives us sort of a theoretical aspect of things. So assume V has dimension 3 and let V1, V2, V3 be a basis for V. So V1, V2, V3 are a basis. That means they're linearly independent and they're a generating set for V. So W1, we're defining 3 vectors. W1 equals to V1, W2 is V1 plus V2, and W3 equals to V1 plus V2 plus V3. Let's check if that's a basis for W. So the question is to check if W1, W2, W3, that forms a basis for V. Of course, first thing I'm going to check linear independence, and I'm going to tell you why this is enough for me to say that it's a basis if you explain it a little bit. So let's check if the vectors w1, w2, and w3 are linearly independent. So that means we write a1 w1 plus a2 w2 plus a3 w3 equals to 0. And if they're linearly independent, then we expect the only solution to be a1 equals 0, a2 equals 0, and a3 equals to 0. So let's see. This is a1 times v1 plus a2 times v1 plus v2 plus a3 times v1 plus v2 plus v3 equals to 0. So we have then a1 plus a2 plus a3 times v1, right? So a1 v1, a2 v1, and a3 v1. Then what's multiplied by v2 is a2 plus a3 v2, and then we have a3 v3 equals to 0. But what do we know about v1, v2, and v3? We know that v1, v2, and v3 are linearly independent, but this is very important. v1, v2, and v3 are linearly independent, which means whenever we have an equation of this form, 100% the coefficient must be 0. So a1 plus a2 plus a3 is 0, a2 plus a3 is 0, and a3 is 0, right? There's no way that we can write an equation like this. So anytime you have alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 equals to 0, because they're linearly independent, the only solution is alpha 1 is 0, alpha 2 is 0, and alpha 3 is 0. So when we solve this, a3 equals to 0, replace it here, you get a2 equals to 0, replace it in the first one, you get a1 equals to 0, a2 equals to 0, and a3 equals to 0 is the only solution. Therefore, w1, w2, w3 are linearly independent. Now, why is that enough for me to say that they span, that they form a basis for R3? So, excuse me. Look, the spanning set of W1, W2, W3, excuse me, is a subspace of V, right? Because these vectors belong to V, right? These vectors are in V, so their span is a subspace of V. Now, because they are linearly independent, the dimension of their span, the dimension of the span W1, W2, W3 is equal to 3. Because there's 3 vectors that are linearly independent, the dimension of the span is 3, because not one of them is a combination of the others. But what is the dimension of V? The dimension of V is also 3. Right? That means it's a subspace of V of the same dimension of V. Therefore, W1, W2, and W3 is a spanning set for V. Is a spanning set for V. And also they're linearly independent. Therefore, they form a basis for V. So, another basis for V would be W1, W2, W3. If you wanted to do this differently, like if you didn't want to do it theoretically this way, you could have checked that they are a generating set. So you could have checked that W1, W2, W3 is a generating set for V. How do you check that? Well, you say for any x in V, for any x belonging to V, am I able to write it? Am I able to write it? So can it be written as, let's say, A1 W1 plus A2 W2 I don't know why I started putting arrows, plus A3W3. Can we write it as X like that? Well, yes we can. Because why? Let's replace W1 by, actually let's do it the other way around. So so that means I can write this as A1. It's that we actually did this calculation here. So A1 W1, A2 W2, and A3 W3 turned out to be this. So you can write this. So this becomes A1 plus A2 plus A3 V1 plus A2 plus A3 V2 plus A3 V3. Right? So any vector that is written like this, in reality it's written like this. So A1, let me think about it backwards. See, I like the theoretical stuff because it doesn't involve all of these calculations, but I wanna show it to you. So let's see. Let's do it the other way. Can it be written as this? So let's just ask ourselves, can it be written as this? Now, what we know is that V1, V2, and V3 is a basis. So X for sure can be written in terms of the basis. So X can be written as alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3. So we are able to write X as this because those are a basis. So can we somehow transform this to make it in terms of W1, W2, W3? So so if we choose A3 equals so if we make A3 equals to W3, A3 equals to alpha 3, if we choose A2 to be alpha 2 plus alpha 3, and if we choose A1 to be alpha 1 plus alpha 2 plus alpha 3, that works. Why does it work? Because look, if you choose, see, those we know that alpha 1, alpha 2, and alpha 3 exist. We know this, right? We know they exist because this is a basis, so this is a generating set and it's linearly independent. My question is, do A1, A2, and A3 exist? Do they exist? Can I find them? And what I'm telling you is, by getting inspired by this, look, if you make A1 is equal to these, so see, these exist. So if I set A1 alpha 1 plus alpha 2 plus alpha 3, and I set A2 is alpha 2 plus alpha 3, and if I alpha 2 minus alpha 3, and alpha 1 minus alpha 2 minus alpha 3, because I need them to cancel. Look at what I get. It's a little bit difficult to see, but once you see what I'm doing, you realize it. So change alpha A3 to alpha 3, so you're gonna get alpha 3 W3. Now change A2 to alpha 2 minus alpha 3. So that would be alpha 2 W2 minus alpha 3 W2. And then this one will be alpha 1 V1 minus alpha 2 W1 minus alpha 3 W1. So and let's see, how does that help me get to this W. W1 is so, and then if I do W1 is equal to V1, so this is alpha 1 V1 minus alpha 2 W1 is V1 minus alpha 3 V1 plus alpha 2 W2 is V1 plus V2 minus alpha 3 alpha 2 minus alpha 3 W2 is V1 plus V2, and then plus alpha 3, and W1 is V1 plus V2 plus V3 is equal to X. Okay, let's see if that reduces to this, and if it does, that we're golden. So let's see. We're gonna get alpha 1 V1 minus alpha 2 V1 minus alpha 3 V1 plus alpha 2 V1 plus alpha 3 V1. So this cancels out this cancels out this, so that's a good sign. We took care of this, and this, and this. Alpha 1 V1 minus alpha 2 V1 minus alpha 3 V1 plus alpha 2 V1 minus alpha 3 V1 plus alpha 3 V1. I'm sorry about this. I thought the calculation would be more straightforward. Alpha 1 V1 minus alpha 2 V2 minus alpha 3 V1 plus alpha 2 times V1 minus V2, V1 plus V2, that's correct. So plus alpha 2 V1 minus, sorry, let me just stop the video so I don't waste your time. I'll figure this out, and then I'll write it down properly, and then I'll show it to you right away, so it's just easier than wasting your time. So here's how this is done. I looked at it a little bit more carefully. We know that the alpha 1, alpha 2, and alpha 3 exist because V1, V2, V3 is a basic. So the alpha 1, alpha 2, and alpha 3 exist such that X is equal to this. The question is, can we find A1, A2, and A3 such that X is equal to those, A1, W1 plus A2, W2. Now, if I replace W1 by whatever V1 is, and I replace W2 by this, and I replace W3 by this, which we did already here, that's going to lead to this equation. So, do A1 and A2 and A3 exist? Well, you transform this equation to this equation, and then that gives you a way to solve for A2 and A1, A1, A2, and A3. So you set A3 equals to alpha 3. So I found A3. I found that A3 is equal to alpha 3. It does exist because alpha 3 exists. I found that A2 plus A3 is alpha 2. So A2 plus A3 is alpha 2. That means I can solve for A2, which is alpha 2 minus A3, and A3 is alpha 3. So I solved for A2. A2 is alpha 3, alpha 2 minus alpha 3. So it's possible to find A2, because remember, alpha 1, alpha 2, and alpha 3 exist. So if I can solve for A1, A2, and A3 in terms of them, then A1 and A2 and A3 exist. And finally, you guessed it, we take A1 plus A2 plus A3 equals to alpha 1. So A1 plus A2 plus A3 is alpha 1. Therefore, A1 is equal to alpha 1 minus A2 minus A3. So A2 is alpha 2 minus alpha 3, and A3 is alpha 3. So A1 is alpha 1 minus alpha 2 plus 2 alpha 3. So A1 and A2, do they exist? Yes, they do. Therefore, W1 W1, W2, W3 is a generating set. We already showed that it's linearly independent, therefore it's a basis. So that's the computational way of doing it. It just took me a second to set it up, but now it's all there. Okay, here's another practice problem about linear independence and generating set and all that, and this came on the final of 2017. Again, some theoretical stuff that helps us focus, helps us maybe do slightly more difficult problems. So let's start with the first part. Just copy it and go to a blank page. So let V, this is again from 2017. Let U and V be in V, assume that U and V are linearly independent, and now let W1 and W2 given by these equations. So let me write them down. So W1 is AU plus BV, and W2 is CU plus DV. Determine precisely the necessary and sufficient conditions such that W1 and W2 are linearly independent. Well, we've done many of this. So let's say alpha 1 W1 plus alpha 2 W2 is equal to 0. So they are linearly independent if alpha 1 is equal to 0 and alpha 2 equals to 0 is the only solution. So let's replace alpha 1 by what it is, by W1 by what it is. So this is AU plus BV. Let's replace W2 by what it is. CU plus DV is equal to 0. So what's multiplied by U? Alpha 1A plus alpha 1A plus alpha 2C times U plus what's multiplied by V? Alpha 1B plus alpha 2D is times V is equal to 0. Now, because U and V are linearly independent, that means this must be 0. The only solution is this is equal to 0 and this is equal to 0. So that means we're going to get alpha 1A plus alpha 2C is equal to 0, and then alpha 1B plus alpha 2D is equal to 0. So we are going to solve this. So let me see, we're solving for alpha 1 and alpha 2. So let's multiply, for example, let's multiply, I'm solving this like the old school way, the high school method. So if I multiply this by minus b, and I multiply this by a, look at what that gives me. That gives me minus ab alpha 1 minus cb or bc, to keep them in order, alpha 2 is equal to 0, and this one is ab alpha 1 plus AD alpha 2 is equal to 0, and then I add them up, right? The cancellation method we learned in high school. That gives me that AD minus BC alpha 2 equals to 0. Now, what I really want is I want alpha 1, alpha 2 equals to 0 to be the only solution. See, I cannot allow a solution that is not alpha 1, alpha 2 equals to 0. So how can I force alpha 2 to be 0? See, what I want, again, I want alpha 2 to be equal to 0 only. So how can I force alpha 2 to be 0? That means that AD minus BC cannot equal to 0. If this cannot equal to 0 and you're multiplying it by alpha 2 and you're getting 0, that means you're forcing alpha 2 is equal to 0. And if alpha 2 is 0, then it's very simple. You put 0 here, and that gets you alpha 1 is equal to 0. So if alpha 2 equals to 0, that would mean that A alpha 1 is 0, and then B alpha 1 is 0, which means we have to assume that A and B are not 0. Right? A and B are not 0? They don't tell us that. But we're going to make sure that A and B are not 0. That means alpha 1 is equal to 0. So, right, A and B can't be 0 because if you multiply by zeros everywhere, you're just canceling the whole thing. So if AD minus BC is 0, that forces alpha 2 to be 0. And if alpha 2 is equal to 0, you replace it on top and you get alpha 1 equals to 0, which would be the only solution to this equation. And therefore, W1 and W2 would be linearly independent. Right? So, by the way, I want you to look at this in a little bit of a different way. Look, if you write this like this, and this is what we're going to do in the live parts where we express matrix multiplication as vectors, a combination of vectors. This is like saying alpha 1 times the vector AB plus alpha 2 times the vector CD equals to 0, 0. Right? And if we want alpha 1 and alpha 2 to be the only solution, if alpha 1 and alpha 2, we want them to be the only solution, that means that AB and CD have to be linearly independent. And if they're linearly independent, it means as a matrix, A, B, C, D, the matrix has an inverse. That means the determinant of this matrix, which is AD minus BC, is not equal to 0, which matches what we got right here. Anyway, that's an alternate way of solving it. You could solve it using this way and you would still be fine. Okay, let's look at the next problem. Just go to a new page. Okay, so let V1 and V2 and V3 are linearly independent. Let W1, W2 equals to, well, it seems to be the same type of problem. So W1 is equal to A V1 plus V2. W2 is A V2 plus V3. And W3 is A V3 plus V1. So we want W1 and W2 and W3 to be linearly independent. So again, we're going to write alpha 1 W1 plus alpha 2 W2 plus alpha 3 W3 equals to 0. And we want alpha 1 equals to 0, alpha 2 equals to 0, and alpha 3 equals to 0 to be the only solution. So let's replace W1 by what it is. It's A V1 plus V2. Let's replace W2 what it is. A V2 plus V3. And let's replace W3 what it is, which is A V3 plus V1 equals to 0. Now let's collect it in terms of V1, V2, and V3. So what's multiplied by V1? There's A alpha 1 plus alpha 3. What's multiplied by V2? So it's alpha 1 plus A alpha 2. What's multiplied by V3? It's alpha 2 plus A alpha 3. So because V1 and V2 and V3 are linearly independent, those vectors are linearly independent, it means that alpha 3 plus A alpha 1 must be 0. Alpha 1 plus A alpha 2 is 0. And alpha 2 plus A alpha 3 is equal to 0. So let's see. Now we want alpha 1 equals to 0, alpha 2 equals to 0, and alpha 3 equals to 0. That means, this is a little bit, so if you want 0, 0, 0 to be the scenario, that means let's pretend alpha 1 and alpha 2 and alpha 3 are our variables. So we're going to get a 0, 1, 1, a 0, and then 0, 1, a times alpha 1, alpha 2, alpha 3 equals to 0. So if you look at it in terms of a system of linear equations, and you want alpha 1, alpha 2, alpha 3 to be 0, that means the kernel of this matrix A, if we call this matrix A, that means the kernel of A is just the 0 vector. Now, this needs a little bit more, this needs the stuff of after the midterm 2. So what you need is basically A to be invertible. Right? You need A to be invertible, so you need the determinant of A not to be equal to 0. I thought we would do it in a different way to make it easier, but it would make it way more complicated. So we need that if alpha 1, alpha 2, if this is the only solution, so if the 0, 0, 0 is the only solution, that means the kernel of A is only the vector 0, which means A is an invertible matrix and the determinant of A is not equal to 0. And we're going to do those in the live sessions, so by the time you're watching this, you would have done determinant and matrices and invertible and all this. So what's the determinant of A? We expand on column 1, on row 1, so A times A squared plus 0 plus 1 times 1. Right, so A times A squared plus 0 plus 1 times 1, and this is not equal to 0, so A cubed plus 1 is not equal to 0, therefore A cubed is not equal to minus 1, so A is not equal to minus 1. Right, so A cubed should not be equal to minus 1 if you want the determinant equal to 0. Again, we're going to talk about all this in details, invertibility and the kernel and all that. We would have talked about it by the time you watched this video, so this would make more sense to you then. Well, then is now for you because you're watching it now. This feels like a sci-fi movie now. So now let's do this. I think we did something similar to this already. So assume that the dimension of V is n. V is linearly independent set. Show that V is a generating set. Right, we want to show that V is a generating set. Now, the idea that the dimension of V is n, and there are there are n vectors that are linearly independent. We talked about this, right? So that means the span of those vectors v1 up to vn, which is a subspace of V, has dimension n, because all of those are linearly independent, which is the same thing as the dimension of V. Therefore, the span of these vectors is equal to V, therefore they are a spanning set. So V1 up to Vn is a spanning set. Now if we want to do it the long way, remember we did this the long way earlier, so let's see, or let's see, so these are linearly independent and the dimension is n, so v1, v2 up to vn is a linearly independent set of maximum size. Why do I say of maximum size? Because the dimension of V is n, and n is the maximum number of linearly independent vectors in V. So you cannot have more linearly independent vectors in there. Those are 0. So how do I know that this is a generating set for V? That means for any vector, so for, look, I'm gonna use like a strange proof here. So for any W in V, right? W is equal to the set that contains V1 up to Vn and W is going to be linearly dependent, right? Because we've reached the maximum number of linearly independent vectors in V. So if I put a vector W in there, that set is going to be linearly dependent. That means there is a non-zero solution to A1V1 plus A2V2 plus ANVN plus BW equals to 0. So there's a solution of this where all of those constants are not 0. So if there isn't, that means they're linearly independent, and that's impossible, right? Because this is the maximum number of linearly independent vectors. So you move, now why is W not equal to 0? Because they can't all be 0. So if W is equal to 0, see, if you make W equals to 0, that means this is equal to 0. And because they are linearly independent, that means A1 equals to 0, A2 is equal to 0. So all of them will be 0. So that means B is 0 and all the other constants is 0, which means the set is independent. But then we know that the set is dependent. Okay, I'm going to say this again. Why do I know that B is not 0? Because if I make B equals to 0, I end up with A1V1 plus A2V2 plus ANVN is equal to 0. Those are linearly independent, so A1 equals to A2, so A1, A2, A3, AN are all 0. And B is also 0 because I set it equal to 0, which means this set would be linearly independent because all the constants turned out to be 0. But this isn't. This is linearly dependent, so we cannot have B equals to 0. So B isn't 0, and that's all we need, because now we can write W as minus A1 over B V1 minus A2 over B V2 minus AN over B Vn. Therefore, V1, V2 up to Vn are a spanning set. Look, for any W in V, I was able to write it as a linear combination of V1 up to Vn. So V1 up to Vn is a generating set, therefore, actually that's what they wanted you to show. If it's a generating set, then it's automatically now a basis. Right? The next proof is a little bit more complete than this. It fits what your teachers like you to do. So maybe just stick to this one. And it's in fact a theorem. I don't know if they allow you to use it or not, but if we have n vectors that are linearly independent in a space of dimension n, then they are automatically a generating set, and we just showed it right here. And if we have n vectors that are a generating set in a space of dimension n, that means they are also linearly independent. So it works either way, but I'm not honestly sure if they allow you to use that theorem or not, so I'm proving it every time. I'd like to look with you now at problems where we have to find the basis and basically find the dimension of some subspace. So consider W, which is a subspace of R3. They're telling us that this is a subspace of R3, but we could also show it if we want to. Now, they're asking us to find a basis for this subspace W. Well, we've done this in the midterm 2 sessions. Let's figure out what W is. So basically W is all the vectors in R3 where x is equal to y plus 2z. So I can rewrite W as all the vectors y plus 2z, y, z, right? For all the y and z that are in R. So basically I can write W as a vector of w's plus a vector of z's, where y and z belongs to R. So this is a vector, so 1, 1z plus 2, 1z. Sorry, I'm just messing this up royally. So we write this as first it's going to be y, then 0, that's the vector of z, plus 2z, then 0, then z. Sorry, I don't know what happened to my brain in those 30 seconds. So it's y, first y, and then no y's, and then 2 z's, no z's, and then 1 z. So I could write the vector this as y times 1, 1, 0 plus z times 2, 0, 1 for all the y's and z that belongs to R. So we can see that clearly W is theoretically the span of the vectors 1, 1, 0 and the vector 2, 0, 1, because it's all the linear combinations of the vectors 1, 1, 0 and 2, 0, 1. So we have a generating set. So basically 1, 1, 0 and 2, 0, 1 is a generating set for W. Now, all that remains is to show that these vectors are linearly independent and therefore they form a basis. Well, clearly 1, 1, 0 is not parallel to 2, 0, 1, therefore they are linearly independent. Remember, in the case of two vectors, if they're not parallel, they're linearly independent. That's special to two vectors. If they're parallel, they're dependent. If they're not parallel, they're linearly independent. Therefore, a basis for W is just those two vectors, 1, 1, 0 and 2, 0, 1. I want to ask you this question. So I want to add an extra note in here about the coordinates with respect to a basis. So let me ask you and let's give you a vector, 5 minus 1, then y plus 2z is 3. Is this vector in W? And if it is, find the coordinates. Let's call this vector x. Find the coordinates of x with respect to the basis that you found in part A. So, what does it mean, the coordinates with respect to a basis? So let's call this V1 and let's call this V2. Right. First of all, is W in X? The answer is yes. So 3, 5 minus 1 is in W because the X component is the Y component plus 2Z. So 3 is equal to 5 plus minus 2. If it's in W, then since this is a basis for W, that means I can write 3, 5. So I can write X as a constant times V1 plus a constant times V2 because those are a basis for W. So any vector in W can be written in terms of that basis as a linear combination. So what are these A and B? A and B, so we call this X is equal to, let's call this basis like funny looking b. So x is equal to the vector AB, like this, so in terms of basis b. So if you express x in basis b, then it's a times v1 plus b times v2. So that means the coordinates of vector x are a and b with respect to basis beta, meaning you can express x as a times the first vector in this basis plus b times the second vector in this basis, and if you had more vectors, then plus c times the third vector, and so on and so forth. So the coordinates of x with respect to a basis, you basically have to write x as a linear combination of the basis vectors, and then the a's and b's, the constants that you use to write that combination, those would be the coordinates of x with respect to that basis. So basically, what are we trying to solve? We're trying to solve 3, 5 minus 1 is equal to a times 1, 1, 0 plus b times 2, 0, 1. This is not so hard to solve. So a plus 2b is 3. A is equal to 5, and then b is equal to minus 1. So if you replace those in here, you check that it's true. So vector x is 5 times the first vector minus 1 times the second vector of the basis. So x is the vector 5 minus 1 in basis beta. So it's 5 times the first vector and then minus 1 times the second vector. In other words, if I ask you this question differently, if I say find vector small w, which is equal to minus 1, 3 with respect to basis b. So what is the vector w that is minus 1, 3 in basis b? Well, that means w is minus v1 plus 3v2. So it's minus 1, 1, 0 plus 3 times 2, 0, 1, which is minus 1 plus 6, 5, minus 1, and then 3. So this is the vector that's minus 1, 3 in basis beta. Right, let's do another example of this. So let's see. Consider V, which is the vector space of infinitely differentiable functions. Let W be the span of these vectors, which is definitely a subspace of V. Any span is a subspace. Now let's find a basis for W. Let's find a basis for W. So we know that this is a generating set, but we don't know if it's independent or not. So let's check if they're independent. So R is the set 1 plus x, x plus x squared, and 1 plus 3x plus 2x squared. Is it linearly independent? Now we can work in terms of the equations. A times 1 plus x plus b times x plus x squared plus c times 1 plus 3x plus 2x squared is equal to 0. And we want to, if they're independent, that means a equals 0, b equals 0, and c equals to 0. So let's check. In terms of constants, we have a plus c. Coefficients of x, we have a plus b plus 3c. And coefficient of x squared, we have b plus 2c. So this is equal to 0 for all x. That means the coefficients must be 0. So a plus c is 0. A plus b plus 2c, 3c is 0. And b plus 2c is equal to 0. This equation gives me a equals to minus c. This equation gives me b equals to minus 2c. And when I replace them in this equation, we're going to get minus c minus 2c plus 3c equals 0. So 0 equals to 0. So a depends on c, b depends on c, but c can be whatever it wants. So a equals to 0. So basically the solution is c is equal to something, parameter, whatever you want. Then a is equal to minus c and b is equal to minus 2c. So this is the solution for any t. This means they are linearly dependent. This means this set, we found solutions other than 0, 0, 0. So this means this set is linearly dependent. So that cannot be a basis. So how do we check which one of these are going to be dependent? I'm going to show you a trick. You can basically take one of them out and try the other two. And how do we see that this is possible? Because let's say c equals to 1 or whatever, minus 1. Then b is 2 and a is 1. That means 1 times 1 plus x plus 2 times x plus x squared minus 1 plus 3x plus 2x squared is equal to 0. That means the 1 plus 3x plus 2x squared is equal to, if you move it to the other side, 1 times 1 plus x plus 2 times x plus x squared. So we can see that this is in the span of the other two. So if you call this V1, V2, and V3, we can see that V3 is in the span of V1 and V2. So we can aim to check that V1 and V2 are linearly independent. So now we have V1, V2 is a generating set because V3 is in V1 and V2 anyway. So V3 doesn't bring any new vectors into the equation. V3 is just in the span of V1 and V2. Now, are they linearly independent? The answer is yes, because they're not parallel. You can see that right away, but let's check. A times 1 plus x plus b times x plus x squared equals to 0. That gives me a plus bx plus bx squared is equal to 0. And if this is 0 for all x, then either a is 0, a has to be 0, a plus b has to be 0, and b has to be 0. So a equals to 0, b equals to 0 is the only solution. Therefore, V1, V2 is a linearly independent set. Therefore, V1, V2 is a basis. Therefore, the dimension of W is equal to 2 because there are 2 vectors in the basis. Right? Now, let f of x equals to x plus 1 squared. Write the coordinates with respect to the basis. So we have the function f equals to x plus 1 squared. We're going to write it as, like, what are their coefficients in terms of the basis b, where the basis b is v1, v2, which are 1 plus x and x plus x squared. So, of course, this needs to be expanded. This is x squared plus 2x plus 1. So we're going to write x squared plus 2x plus 1 as a times the first vector plus b times the second vector. Of course, we're given that this is in W. So let's see. We're going to get x squared plus 2x plus 1 is equal to a plus bx plus bx squared. So the constant should be 1, so a is equal to 1. The coefficient of x squared should be the coefficient of x squared, so b equals to 1. And then a plus b should be 2. Well, what do you know? If a is equal to 1, then a plus b is, a is 1, b is 1, so a plus b is 2. So therefore, this f, which is x plus 1 squared, is 1 times 1 plus x plus 1 times x plus x squared, which means it's the vector 1, 1 in the basis b. So this is being the basis b. Right? And that's how we find the coordinates of a vector with respect to a basis. That's how we find the basis. That's just some practice of basically midterm 2 material.